Let's move on now to the technique of jitter measurements made during voluntary activation. To measure jitter during voluntary activation, the electrode is placed so that it is recording with adequate amplitude and rise time action potentials from two muscle fibers that are activated by the same motor unit. This is done during slight voluntary activation. So every time the patient activates motor unit A, both of these muscle fibers fire, and we put the electrode into the muscle and move it around very slightly until we find a position where we can see two spikes that are time locked. And because they're time locked, we know they're coming from the same motor unit. And I would emphasize that this position is different from the position that's used for fiber density measurements. With fiber density measurements, you want to put the electrode as close as possible to one muscle fiber. Maximize the amplitude of that one muscle fiber. With jitter measurements, you want to be in a position where you get good amplitude from two fibers, which is usually not the position when either one of them is of maximum amplitude. Both of them must produce signals of adequate amplitude, however. Because these electrode positions are different, and because you can influence the fiber density measurement if you're not consciously putting the electrode as close as possible to one muscle fiber, you need to mentally separate two processes. The best way to do that is to make them at different times, temporally separate them. In other words, do your fiber density measurement first in the muscle and then do a jitter measurement. There are two techniques for measuring jitter. One relies on measurement of the time at which an action potential reaches a voltage threshold, and the other one is based on measuring the time at which occurs the peak of an action potential. This slide shows the technique of voltage threshold measurement. These are a number on superimposition because they're coming from the same motor unit. They always fire together. And the trigger point at which we acquired these signals is on the rising phase of this first spike. Therefore, it's frozen on the screen. The second spike varies slightly because of the neuromuscular jitter. These windows here represent points at which each of these signals is timed. The point on the first signal that goes through this threshold starts a clock, and the point at which the following potential goes through the second window stops the clock, and then the clock reading is stored in the computer. And this happens for all of these pairs of potentials that are occurring during this epoch. The histogram down here, this sequential histogram, plots the value of each of these intervals. The interval between spike 1 and spike 2 is the interpotential interval of that discharge. And this plot down here shows the value of the sequential interpotential intervals during this time epoch. These intervals do vary a little bit in their timing. This is not a flat line. And this variability in this bottom plot is the neuromuscular jitter. The technique that uses the peak amplitude to measure the timing is diagrammed here. First of all, the pair of potentials is acquired by setting a trigger level. And the machine then looks at these spikes and plots the slope of the rising and the falling phase up to their intersection point and takes that point as the start of the clock. It does the same thing with the following spike, and that point in time is where the clock stops. And then the jitter is measured between these calculated peaks. There's some practical and some theoretical differences in these two techniques. This is one of the advantages of the peak detection technique in that because of slight variability in the baseline, any action potential is going to rise up and down a little bit. And because the rising phase is not vertical, the time at which it cuts the voltage trigger is going to vary slightly just because of the baseline variability. So this is a characteristic that's inherent in the voltage threshold technique that is not there in the peak detection technique. Another advantage is shown here when you have two action potentials that are very close together. Because of the interaction between the falling phase of the first and the rising phase of the second, the slope of the second potential will vary because of the summation of these signals. And so measuring time between any voltage change of the second potential would be spurious. But the peak detection algorithm doesn't have that problem. So you can measure jitter in close potentials better with the peak detection than with the voltage detection algorithm. These are the two things that can be recorded during jitter measurements. One is the interpotential interval. Interpotential interval is the time between 1 to 2, 1 to 2, 1 to 2, 1 to 2. The interdischarge interval is the time between the discharges of the pair of potentials. The jitter is measured from variability in the IPI, and the IDI is a way in which we measure the firing rate. Jitter is calculated from this formula as the mean difference between consecutive interpotential intervals, and this is the formula for that down here. We take the first interpotential interval here, subtract the second interpotential interval here, and take the absolute value of it and add it to our buffer. We then take the interpotential interval 2 and subtract it from interpotential interval 3 and put that absolute value in our buffer. We continue doing that during the entire sequence, add up all of those differences and divide by n-1, and that gives you the mean difference between consecutive interpotential intervals. Why do we go through this exercise? Why not just take the standard deviation or some other measure, simple measure of variability? And that's because of trends in the data. The intervals may show a slight steady increase or decrease during the time that you're measuring them. And if you used something like standard deviation, then that trend would affect your calculation. And that trend is minimized by measuring the MCD. There's another measurement called the MSD, mean difference between sorted interpotential intervals. It is measured to minimize the effect that variability in firing rate has on the jitter calculation. Within a given muscle in a disease like myasthenia gravis, there's variability in the amount of jitter in different end plates. Here, for example, is a pair of potentials in a muscle where the jitter is normal, and here's another one in which the jitter is increased, and another one in which the jitter is increased and there's marked blocking. One of the impulses fails to occur from time to time. In order to describe the overall jitter within a muscle, there are a number of measurements that are of value. First is that you can take the mean jitter of all of the measurements that you've made in that muscle and use that as the measure of central tendency in the muscle. However, mean values are markedly affected by outliers. So if you have just a few or end plates or pairs of potentials in the muscle that have extreme values, it'll drive up your mean. To overcome that, you could use the median value of these, and that reduces the effect of outliers. Another way of doing that is to look at the percentage of the measurements that you made in which there was some blocking. And you can also look at the number of measurements that you make in which the jitter is within a normal limit. And all of these observations are useful under some circumstances, and this is one way to display the data. This is a histogram of the jitter measurements made within a muscle, looking at jitter in 20 different pairs of potentials. This is just the number of pairs of potentials in which the jitter was of a certain value. And the dotted line here is the upper limit of normal for the individual pairs of potentials. And you can see that all but one of these pairs of potentials fell to the left of the dotted line and therefore was normal. The mean value was 28 microseconds. The median was almost the same, 32. 95% were normal and there was no blocking. Compare this with a similar plot made from a patient with myasthenia gravis. Same upper limit of normal, you can see that a number of the recordings had values that were outside the normal limit, and one pair potential over here had blocking. So the mean value and the median were around 55, 60, 70% of the pairs were normal. I showed the sequential histogram earlier. This is the way the histogram is plotted in the Synergy equipment. In the key point equipment, it's plotted vertically, but you get the same information from this line of dots that you get from this line of dots. The line of dots shows you things like the amount of jitter, whether they're trends, effects of firing rate, and outliers. This is a normal sequential histogram with a relatively tight line of dots. Here's a plot that you would get when there's increased jitter. The thickness of the line of dots reflects the increase in the amount of jitter. This is an interesting, unusual phenomenon called bimodal jitter, in which the intervals between these pair potentials varied between two stable positions. And just to show you the sequential histogram here of these measurements, clearly these values represent two different populations, and you can see the same information from this non-sequential histogram of the same data.